Hello students, today we are going to see that is a topic electromagnetic wave. So in this topic we are going to see about the introduction about electromagnetic wave. What is the source of your electromagnetic wave? Then again we are going to talk about your Maxwell displacement current, then Hertz experiment. Then again we are just going to talk about the various terms related to that your electromagnetic wave, then Maxwell equation and your electromagnetic spectrum. So till now, if I just consider that electromagnetic wave, so it is a simple the combination of your electric field and magnetic field, and which is going to propagate in a particular direction. We are just going to see it in detail, but if you see from this diagram over here, so that is electric and magnetic field, they are perpendicular to each other at the same time, so they are propagating in a particular direction. So this is how we can show this your electromagnetic waves over here. Now we are going to see what is that Maxwell displacement current. So this is nothing but related to your Ampere's circuital law. Now we know that in the Ampere circuital law, so what we had just seen that if I just take this is, let's say, a current carrying conductor through which the current I is flowing, and we know that since it is a source of magnetic field, it is going to produce the magnetic field around it. Again, its direction, you know that it is according to your right hand, that is a thumb rule. So what we have to do for this particular case, so that is your integration of your B bar dot dl bar, so which is nothing but mu naught times the current enclosed by that path. So this is how we define that your Maxwell related, that means Ampere circuital law over here. So with the help of this we can say that, so this is a current carrying conductor, so the conductor has to be present over there and which is associated with the magnetic field, and you have to just evaluate the value of B at every point over here. So you will get, so that is nothing but the mu naught times the current enclosed over there. Now the same thing if I just, let's say, consider for a case of capacitor. So this capacitor I'm just going to connect it across, let's say, some potential difference over here. Now what I know that, so the charge starts to build up on this your plates. On the first one you can say that the plus, and according to similarly on the second one it is a minus. Now what I will do, so if I just take a magnetic needle and if I keep it over there, so near to this end over here, so I found that obviously this needle has got deflected. Now again a very interesting thing that I'm going to do, so if I just place that needle, if I just place that needle in between these two plates, yeah, so I'm just going to place it in between these two plates over here, still I found that it has got deflected. So I found that this needle again it has got deflected over here. So when I just keep it between these two plates of your capacitor, so how it happens, so I know that for this at this point definitely there was a current carrying conductor near to that, and that's why you can say that, so the current carrying conductor will produces the magnetic field, and according to that the needle has got deflected. But between these two plates of your capacitor, obviously you can say that there is no physical current carrying conductor, but still the needle has got deflected. So how it happens for this particular case? So now just to find that particular case, so it is related to your electric field and magnetic field. So what I know that a current carrying conductor is the source of your magnetic field. Again I know that a change in the magnetic field also can produce the EMF. So according to the relation, E is equals to minus d phi by dt over here. So now again what happens for this particular case over here, so as the charge starts to build on these two plates, so what is going to happen, so definitely the flux link with this loop, yeah, so definitely the flux link with this area, so that is nothing but phi is equals to, again I know that that is a E bar dot A bar. So this is what I know that phi is equals to E bar dot A bar. Again I can say, let's say phi is equals to E into A. Now the field between these two plates, now we know the value of E, that is between the two plates of your this capacitor. So that is E is equals to sigma upon epsilon naught. Again, sigma is equals to Q upon A epsilon naught. So phi, you can say that, so that is a Q upon A epsilon naught, again multiply by that A. So this is Q upon epsilon naught. So what you will get, so this Q is equals to epsilon naught into phi. So I want to find that is a I, so which is nothing but dq upon dt. So this is your epsilon naught into d phi by dt. So what you can say from this case, obviously the flux which is linked to this your area, it is continuously changing for this particular case, and because of which the current is also getting changed. If the current is getting changed, obviously you can say that the field is getting changed, the electric field is getting changed, and which will change your magnetic field. So that is how we can correlate all these things over here. So the electric field, a change in the electric field is associated with the change in the magnetic field, and because of which this needle has got deflected. So that means, so the electric field between these two plates is getting changed. So since the charge is continuously starts accumulating on those plates, so the charge, it is a process where the charge is keeps on building, so which will just change the electric field, and the change in electric field is also simultaneously associated with the change in the magnetic field, and that's why we can say that the needle has got deflected. So this kind of current we are going to call it as nothing but obviously the displacement current, and which is related, or you can say that it is epsilon naught and d phi by dt. So what is that modification now? So this modification, so where we have introduced that your displacement current, so that is in addition to that of your conduction current whenever the electric field and flux changes with the time. So for this case, obviously the integration of your b bar dot dl bar, so which is nothing but mu naught IC plus your mu naught ID. So that is your displacement current. So this is how you can modify this law over here. So in displacement current, obviously we don't require that physical medium, we don't require that actual conductor over there. So if even the field between those two plates, if it is changing over there, so the field is getting changed, so simultaneously because of that the magnetic field also gets changed, and that is how the needle gets deflected. So that is the modification that we have done in this case of your Maxwell displacement current. So now, so the same thing, so that is a consistency of your modify Ampere's law, so where we just include that of your conduction current as well as displacement current. So that is nothing but your sum of your IC and ID.